Hello and welcome to the lesson on elastic and inelastic collisions. So your goal today, I can differentiate between elastic and inelastic collisions. So something that's very important to be able to do. And then you can complete the associated or the correct calculations for that particular application. You'll notice there's a couple of videos. This is a longer lesson than some of the previous ones. And that's because there's a proof in here that I want to go through. And the proof, I think, in my opinion, is very important. As you go into university or college, you're going to be subjected to some theoretical stuff, some proofs, so it's good for you to see from time to time. So while I'm not looking for regurgitation, I do want you to be able to follow through and say at least that you could understand or see the steps involved for developing the formulas that we're going to use. So keep that in mind. So going through our note that we have for you. We've talked about two laws of conservation. In the grade 11 course, we talked about the law of energy or conservation of energy. And now in grade 12, we're talking about the conservation of momentum. So there's your momentum, conservation of momentum. There is our conservation of energy. Get some vector symbols drawn in there. MGH, K, I guess X, so on and so forth. So there are the formulas that we talked about in terms of conservation of momentum and our conservation of energy. So there are a couple of things we're going to revisit here. There are two types of collisions that we're worried about, and it's in the goal of this particular lesson, and that's elastic and inelastic. So here are you have the definitions in the note. Elastic collisions occur when both kinetic energy and momentum are conserved. All right, so in this scenario here, the kinetic energy prior to collision is equal to kinetic energy after collision, and our momentum is also conserved. So our change in momentum before is equal to our total momentum after. Inelastic collisions only occur when momentum is conserved. All right, so for this one, it's only when the momentum is equal to the before and after. So what's happened is there's been some deformation or energy transfer. And it could be sound energy, could be heat energy, but some form of energy transfer has occurred. All right, so the nice thing with the inelastic collisions, we've really just been talking about inelastic collisions for the first part of this unit because we've been just talking about momentum. We've assumed things have been colliding together, and we've only analyzed it from a momentum perspective. Elastic collisions require us to do a double analysis. So as we go through, we are going to look at exactly how they're related together. And what we can do is we can combine that information together. The elastic and inelastic and the kinetic energy and the momentum can be combined together in order to give us one final formula rather than going through multiple steps to get to a final answer. So here's one of the proofs, or the proof I was referring to, and I'm going to show you how the equations are developed for our elastic collisions. So for momentum, we're just going to look at two objects interacting. So we know that we have this particular formula, V1 prime plus M2 V2 prime. And then from a kinetic energy standpoint, we have the 1/2 M1 V1 squared plus 1/2 M2 V2 squared. That's going to equal 1/2 M1 V1 prime squared plus 1/2 M2 V2 prime squared. So those are the two formulas that we want to look at and see how they interact with each other. So for both equations, what we're going to do is we assume the final velocity of the second object is 0. So we assume V2 equals 0 meters per second. What that is we're really going through a change in frame of reference, and we'll talk about that and how that works in some of the examples later on here. So if we make that assumption that the final velocity, if we assume V2 is 0, that means that that term drops out of our equation. Similarly, this term will drop out of our equation. So our momentum that we're analyzing now becomes m1 v1 equal to m1 v1 prime plus m2 v2 prime. And the other one, every term has a half in it, so I'm going to drop that one halves. All right, which reduces the kinetic energy formula to m1 v1 squared equal to m1 v1 prime squared plus m2 v2 prime squared. So those are the two formulas that we're going to manipulate here. My goal, or my ultimate goal, is I want to find something that's in common. So this is something that obviously I wouldn't expect you to be able to do. So that's why I'm demonstrating it to you, and you can kind of follow along. So for the first equation here, I want to get all the like terms together. So both sides of this equation have an m1 term. So I'm going to collect the v1 or the m1s on the same side. So my formula is going to look like this, and I can factor an m1 out, leaving me with v1 minus v1 prime. That's equal to m2 v2 prime. I'm going to leave it at that. On the other side, it's the same thing. m1 is common, so I'm going to move that term to the other side. So remember, I'm manipulating two formulas, and I want to find a relationship between them and combine them together to make our life easier when we're dealing with elastic collisions. That's the ultimate goal here. I'm going to end up with one equation in the end, and I just want to show you how I get from point A to point B. Again, take out the first mass, you get v1 squared minus v1 prime squared equals m2 v2 prime squared. So there we are. I've simplified the formulas into a form that I want. Now your note you have, I believe the next page is blank, so you can just continue on. I'm just going to keep working down. It's a little easier for me. So what I want to do is I want to find the ratio of kinetic energy to change in momentum, which essentially means what I'm going to do is I'm going to put the, I'm going to stack my formulas in that fashion such that, in brackets here, I'm going to put my EK over delta P. So I'm going to find the relationship that exists. So, extend my page here. So I put the, now we're dealing with the combined formula. So here's the kinetic energy, or the right formula. So v1 squared minus v1 prime squared. And that's going to be put over m1 v1 minus v1 prime. So that's the left side of the equation. Excuse me. m2 over v2 prime squared. And put that over the m2 v2 prime. Now when we set up as a ratio, what happens is that the masses will fall out on both sides, and now I'm left with just the expression with velocities. So those expressions with velocity, if you take a look at the numerator, I have v1 squared minus v1 prime squared. It's actually a difference of squares. So a grade 10 concept. Both the first and the second term are perfect squares. There's only two terms, and there's subtracting involved. So on that top, it is a difference of squares, and I'm sure most of you are saying, well, I would never have seen that. And that's fine. I wouldn't expect it. That's, again, why I'm doing this out in full for you. But it is a difference of squares because, again, the first and last term are squared, and there's subtraction in between. Oops. So what that allows us to do then is to cancel some terms out here. V2 prime. And actually, well, I'll do it in the next step. The right side, I can reduce that as well. So what does that reduce or cancel out for us? That term then disappears, and all we're left with is v1 plus v1 prime equals, these are like terms on this side. I just kind of neglected it in that last step. So we're reducing it down to v2 prime. And there we are. So that tells us that if in an elastic situation, that v2 prime, the final velocity of the second object is equal to the velocity of the first object plus the final velocity of that first object. So what we can now do with that, we can take that information back, and I'm going to work sideways here. You can continue filling out your page. We're almost done here. So if we look back to the earlier formula, M1 V1 minus V1 prime equals M2 V2 prime. We can do that substitution because now we know what V2 prime is equal to. We just figured that out. It's in the green box. So M1 V1 minus V1 prime equals M2 bracket V1 plus V1 prime. So now I'm just going to quickly distribute and collect like terms. So M1 V1 minus M1 V1 prime equals M2 V1 plus M2 V1 prime. And what I'm going to do is I'm going to isolate for V1 prime here. So I'm going to leave it or move it to the other side. So I'm going to have M1 V1. So I want to know how to calculate that final velocity of the initial object minus M2 V1 equals, on the other side then, it would be M1 V1 prime plus M2 V1 prime. And on the other side as well, I find out I have V1's common here. So V1, M1 minus M2. And on the other side, I can take out a V1 prime, and I have M1 plus M2. So now I can solve for one of the terms, and I'm going to isolate the V1 prime because I want to know, usually we're given the initial conditions, we're given V1. So I'm going to divide both sides by the M1 plus M2. And that gives us our final formula here. So therefore, the final velocity of the first object is going to equal the initial velocity multiplied by M1 minus M2 divided by M1 plus M2. So there is your secondary formula here. So I'm not going to do the final proof here because I've taken up a full video here. So your final formulas then. So you've already got one there. So the other one, I'm not going to bother going through the proof because I've gone through the process. You get the general idea. So the final velocity in an elastic collision for the first object will be its initial velocity, M1 minus M2, divided by M1 plus M2. And to find the final velocity of the second object, which we assumed was at rest, is the initial velocity of the first one. And this is the one I didn't bother proving, and I'm saying I've used up enough of your time and probably enough of your attention at this point. So there are the two formulas you definitely want to get added onto your cheat sheet, and that is for elastic collisions. All right, so elastic collisions where energy is conserved. All right. So that, like I said, the proof, it's important that you get to see a proof at this level because you are going to come across proofs in your university/college careers. So it is important that you get a chance to see what it's going to be like. You may not enjoy it, but be forewarned, if you're signing up and taking a chemistry or biology or physics or a math course at college or university, you are going to see this from time to time. So you need to be able to at least follow it through. And that's all I really want you to be able to do is follow the substitution. Can you do all the math? Absolutely. But I know it makes it challenging when you're not really sure where you're heading. It makes a difference because the people who develop this kind of stuff, they have a goal in mind. They know they're looking for the final velocity and so on and so forth. So anyhow, the next video, I still have a couple things I want to go through. So you're looking at, I understand it's going to be a little bit longer than other videos. So we'll go from there.